Hello, we're gonna start this lesson GPU programming in Nvidia PTX, where basically PTX is Nvidia's GPU assembly language. There is an intermediate representation between CUDA and the hardware. CUDA is the programming language of Nvidia GPUs, where an analogy with normal CPU compilation. It's an intermediate representation like LLVM, where this is an intermediate representation that is well, in the case of LLVM, it creates like a kind of virtual machine intermediate representation that is hardware agnostic, that then it goes to the execution in the real hardware. In the case of PTX, the real hardware instruction will be SASS and then the GPU execution. And this allows low level optimization and hardware control. CPU versus GPU architecture. In the case of CPU, we have few complex cores optimized for latency, while in GPU, we have thousands of simple cores optimized for throughput, and GPU executes thousands of threads in parallel. Before continue, we have to see kind of a hierarchy that we have in GPU, where we have a streaming multiprocessor that basically we have SM, that is the streaming multiprocessor. That is kind of like the microarchitecture of our NVIDIA GPU. In my case, I have like a 4090. So I will have a streaming multiprocessor 89. And then in this complex cores, we have a warp where these are basically 32 threads. So they work as a group of threads that are in the core executing instructions in parallel. And then we have the smallest unit that is just the thread. So in the streaming multiprocessor, we have the microarchitecture where we have the cores, the registers, and so on. I have warps, groups of 32 threads running in the cores, and we have the smallest unit that is a thread. In the case of warps, as we have these threads, we have the concept of SIMT, that is single instruction multiple thread, where we have multiple threads executing the same instruction in parallel. If we want to see a little bit more about like the architecture and so on, we can see this in NVIDIA SMI, and here we can see the CUDA version. We can see also, let's see, okay, here we see the model of the GPU and some metrics of what's going on here, the usage and so on. So having said this, I want to run a query to see what is my microarchitecture in the streaming multiprocessor. Here I have this window. Well, I have WSL, so I have CUDA in both in my native operating system in Windows and also in my WSL, so we can see like in Windows I'm using way more the GPU. I have more utilization here, more power in my usage in comparison, to see like a metric here. I'm using more power and so on. So in order to see this, I'm gonna show real quickly script that I have here. This code in CUDA, including the library of CUDA runtime, we can see the device properties where we have, well, in my case, I only have one GPU, so my device ID will be 0 by default. So here in this function, I just insert the properties that is going to be over, like reading this variable with this reference, and I'm just going to uh, store here all the properties of my single GPU. I will have the property name, the GPU name, and the number of the multiprocessor count that will be my SM. So here I will just run the compilation of my code, and I will run this. So running this script, I can see that I have uh, 76 stream multiprocessors. And I can see here the name of my GPU as well. Also here in this code, okay, let me add this here. Here I can get um, like more insights about my streaming multiprocessor and so on. So continue with this presentation. We see like the level of hierarchy is basically we have the streaming multiprocessor. In each core we have warps, there are groups of 32 threads running the same instruction, and then we have the smallest units that are threads. Here we see that we have in the streaming multiprocessor, we have is the core computing in Nvidia GPUs. This contains the CUDA cores, the tensor core, the registers, and the shared memory. And this runs in threads of blocks that are the warps that we already saw. And the streaming multiprocessor version of GPU, the microarchitecture. This is equivalent to the CPU microarchitecture, where we have examples of the stream multiprocessor of Ampere. We have Adaloff Plus, like is the same architecture that I have. And this defines the hardware capabilities. This is my GPU, so this supports 4th generation of tensor cores, and this is optimized for AI and deep learning workloads. Why does the version of a streaming multiprocessor matters? These controls supported instructions, controls performance optimizations, and required for tensor core instructions. Tensor core instructions are a special hardware for matrix multiplication, accelerates deep learning, and here's we're gonna see an example of this code in PTX instructions later on. We see that we're gonna see a little about the syntax of PTX code, where we need to specify the version of PTX. We need to target the specific GPU architecture, and the entry is the kernel function, where in GPU, every function, every function that we pass parameters and it's like execution operation is a kernel. And here we see the registers in PTX, where this is the fastest memory in GPU declares using the keyword rect directive, and it's used for arithmetic operations. Here we see some memory types in the GPU where we have registers that are the fastest. We have also shared memory that is fast and global memory that is slow but is large. So it's an analogy with the same hierarchy of memory that we have in the CPU, where we have the disk, we have the RAM memory, we have the cache, and so on. So in this case, we have different levels in the hierarchy where the registers are the closest, they're the fastest, and then we have also constant registers that they are like the fastest too, with they are read only. So we're gonna see this later. We see the thread hierarchy. We have threads that is the smallest unit. We have warps that are 32 threads, blocks, and grids, where we have grid is a group of blocks, and a block contains multiple threads inside of it. We see the parallel execution model where all threads execute the same instruction. Each thread has different data, and this is the single instruction multiple thread model. I want to go through this briefly, and then we're gonna see some code examples. In the control flow, we have conditional execution using predicates, branch instructions, and loop supported. What happens here is that warps the function in groups. So when we have control flow like an if-else statement, we see like this is serial, like in a CPU manner, where we are gonna follow a branch based on the input on the condition. So if we have, for example, a flag like I equals 0, then execute an instruction, we are only gonna execute one of these branches. So that makes some waste in some of the code that will be executing the another instructions that is not gonna be executed based on the if condition. That's why data structures like trees are do not go well in the execution in GPUs. So you have more better optimization and more performance using the tensor cores with conditional execution. We use predicates, where basically we mask out some of the results that wouldn't be used in the branch, and we're gonna see later on. Here we see the compilation flow when we have CUDA, that is the highest level programming language of the GPU. Then we have PTX, then ASSS, that is real hardware instructions, and then the GPU execution, where we have PTX that is compiled to hardware instructions. Why PTX is important? These optimize AI inference, improve performance, write custom GPU kernels. And here we can see some of the applications. We're gonna then do some code examples.